Behold ferrofluid in a bottle, one of the coolest office curios, period. You can spike it, toss it, drop it, pull it, bridge it, and make it dance. Ferrofluid is a liquid that responds to magnetic fields. It consists of nanoscale iron particles suspended in a liquid carrier. Untouched, the liquid forms in a smooth pool, but by applying a magnetic field, it reacts in strange and fascinating ways. That's science. Ferrofluid in a bottle is sealed in a 60 milliliter glass bottle, along with the suspension liquid.
Ooh, like cologne for the brain.
The transparent liquid and the ferrofluid won't mix, but they will form a mesmerizing interactive display that will capture your attention for a very long time.
Hey, I'm locking the front door. Anybody still here?
Yes, sir. The numbers are looking very positive.
This thing is a bottle of pure awesome. The set includes 2 rare earth magnets to manipulate your ferrofluid. Buy ferrofluid in a bottle now at VAT19.com.
VAT19.com.
Oh, hey. So yeah, magnets can do that. Don't forget that red slides are where you have to take notes. You should have your notes handout ready to go. Don't forget to look for the owl and let me know where he is. And remember to fill in all of this stuff that you see here. All right, so this week we're going to be talking about magnets and electromagnetism. So first let's talk about magnets, regular magnets, and what exactly they are and how they work. So magnetism is the force produced by a magnetic field. These are electric charges in motion. We kind of know some stuff about electric charges so far. We know that they have to do with electrons and the way electrons move and things like that. And we understand that electrons can repel and attract things. So that's basically what magnetism is. And a magnet is an object or a device that gives off an external magnetic field. And that magnetic field might look something like that. Now, okay. That's the definition that I've given you so far, but that's kind of a bad definition. I mean, think about it. This is like somebody saying, so what exactly is magnetism? And the answer is, well, it's the force exerted by a magnetic field. And what exactly is a magnetic field? Well, it's the thing that's created by magnetism. So magnetism is magnetism? Yeah. I don't no, that's not a good definition. Let's try to figure this out a little bit better here. This is a better definition, but a little bit more complicated. So I want you to think of it like this. I'm going to use an analogy here. So imagine 2 kids are trying to pull a wagon. One pulls from one side, the other pulls from the opposite side. Well, think about what's going to happen there. The wagon doesn't really move at all, right? So, and that's because one of these guys is pulling in that direction, right? And the other guy is pulling in that direction, and these forces are going to kind of cancel each other out. Well, now imagine that the 2 kids realize it isn't working and they switch positions, so they both pull from the same side. Well, what's going to happen here? Yeah, the wagon is going to move, right? All right, so wait, are we supposed to be talking about magnets here? Okay. Yeah, I'm getting a little lost too. Okay, gotcha. So everything around you is made up of tiny particles, right? And one of those particles is called electrons. That's these guys right here, electrons. So, all right. So as the name suggests, electrons have an electrical charge. That's where the word electrical comes from. And whenever electricity moves, a magnetic field is created. So, okay, so you're made up of electrons, you're made up of all these little particles. So if these electrons are in everything and they're magnetic, well, how come only some metals are magnetic and not, for example, your dog or something like that? Why isn't everything magnetic? Why doesn't everything kind of stick to everything else if everything's made of these things? Well, okay, I want you to think back to the examples of the kids pulling the wagon. Most things, the electrons send their magnetic pull in different directions. So they're kind of like the two kids pulling in different directions. It's very chaotic and random. They're all pulling in different directions. And so just like the kids with the wagon, if they're all pulling in different opposite directions from each other, they all kind of cancel each other out and no movement happens. And try to remember here the idea that that's kind of what magnets do. They make things move, right? So, okay, so what we need to do here is we need to get all of these little electrons to pull in the same direction. So here's your better definition. In metals that are magnetic, the electrons are all sort of facing the same way. So when they all pull in the same direction, that can get things to move. So these electrons all sort of pulling in the same direction. That's really what magnetism is, and it has to do with electrons. So magnets are kind of cool. You saw some good stuff that they did at the beginning of this video. So what else can magnets do? Well, they can do this. So this is a picture of the United States, obviously, and this is a picture from space at night, and you can see all the lights. I think this is a really cool picture. First of all, it kind of shows where the population density is in the United States, where most people live. You can see that clearly they tend to live, they're very packed in near the water, and over here as well, near the water. And there seems to be a lot more people on the eastern side of the country, and then it kind of fades out in this area. Well, you guys know that there's lots of deserts out here and things like that. And I think it also it has to do with the history of the United States. If you remember, the Pilgrims came over and settled this area first, and then they started moving out west slowly, right? And it's almost like we're still kind of doing that, but we've basically kind of colonized the whole United States, and left these areas alone. But I bet you 50 years from now, there's going to be a whole lot more lights in this area. Anyway, back to the subject. So all of these lights, well, what do I mean? What do magnets have to do with this? Well, here is a power plant, right? And power plants, electrical power plants, well, they make electricity. And sort of a key part of this is that magnets are really the most important part of that. So we see some smoke coming out of the top here, and you might think, well, what are they burning in there? Well, it could be a lot of different things depending on what kind of power plant this is. But basically the idea is what they're burning something, they're heating something up to boil water. That's the basic idea. They're trying to boil water, and the whole point here is to get a magnet to move. If we can get a magnet to move, we can make electricity. So how does this work? Well, you might remember this, okay? So as soon as I showed you this picture, you might have had a little heart palpitation there thinking back to this and thinking, oh, geez, back to what is this again? Oh, the electromagnetic spectrum, right. So it's called the electromagnetic spectrum because, well, it's got an electric field and a magnetic field. And notice that they go together. No, I'm not going to make you draw this again, don't worry. They kind of go together. They're all part of one wave, and so you can understand this idea that electricity and magnetism are related to each other. In fact, they're kind of part of the same thing. They're just two different ways of talking about the same thing. So this kind of makes sense that magnetism and electricity would be related. And remember, our definition of magnetism has to do with electrons. And of course, electricity also has to do with electrons. So how does this work? Well, okay. Here is a guy that's really, really important. This is Michael Faraday right here. Really important guy. He's basically the guy that figured all this stuff out. He's the guy that figured out how we get electricity. And really one of the most important things that he figured out is this idea right here, that if you take a magnet and you take a coil of wire, so a wire that's kind of wrapped around in some loops like this, and if you take the magnet and move it within that coil of wire, look what we get here. We get electricity. We get a voltage on this meter. And if you look at this carefully, you can see that we only get the voltage when the magnet is moving, not when it's staying still. You can't just stick a magnet in there and get electricity. You have to move the magnet back and forth. Well, why is this happening? Well, if we take a closer look at this wire, kind of looks like that right there. And if we take a even closer look, well, we remember that this is made of metal, and metal is a conductor. And what does that mean? Well, it means that it allows electrons to flow through it. So these electrons aren't really held on too tightly by these atoms, and the electrons are allowed to move through this wire if you make them move. Well, remember that magnets have to do with electrons and getting them the electrons to kind of move around, right? So as you move this magnet through this coil of wire here, it basically forces the little electrons in there to start moving. And of course, at this point, you should be saying moving electrons. I know what that is. That's electricity. Okay, so Faraday's law of induction is that the changing of a magnetic field can create voltage. By the way, that's what that word means, induction. Okay, that's all it means. This definition of Faraday's law of induction is also a definition of the word induction. It's just the idea of making electricity with magnets. So that's the idea. Faraday's law of induction. Very, very important idea. This is why we have electricity at our houses, because Michael Faraday figured this out. All right, so the other side of this is that you can have things called electromagnets. And I want you to think of this as basically just the reverse of what we were talking about before. Remember, before what we did was we moved a magnet in a coil of wire to produce some electricity. Well, in this case, if you take some electricity and move and create some electricity in a coil of wire and you put a piece of metal inside of that, you have yourself a magnet. So in other words, this idea of electromagnets, that by running electric current through a wire you can create a magnetic field, is just the opposite of Michael Faraday's idea. It's the reverse of that. Michael Faraday figured out that with a magnet you can create electricity. Electromagnets are just using electricity to create a magnet. It's just two sides of the same coin here. It's either it's electricity and magnetism. They are both sort of connected to each other, and you can use magnets to create electricity, or you can use electricity to create a magnet. So what are the implications of this? Well, this is, again, very important here. This has to do with what we call electric generators and electric motors. So let's start off with the idea of electric generators. This is an electric generator right here, and you've probably heard the word generate before, and that means to make something, right? So electrical generators, well, they make electricity. They generate electricity. And this is probably one of the most well-known, most famous examples of this. You may have seen this before. You might know what this is. This is Niagara Falls. There's the falls right there, like you might have seen them before. This is sort of a historical picture of when they put a dam in the falls and turned it into an electric power plant. And the whole idea here is we're going to use all of this movement, all of this energy from this flowing, falling water, and we're going to make it move some magnets, right? And all of these guys here, these are what are called turbines here, there, and all the way down the line here. These are turbines, and all they're doing is basically the water is making these guys spin around and around. And guess what's in there? A magnet, right? And so if we have a coil of wire and a magnet, and we make the water spin that magnet around, what do we get? We get electricity, right? Just like Michael Faraday said. So an electric generator creates electricity by moving a magnet through a coil of wire. This is our idea of Faraday's law of induction, right? And this is what we call an electric generator. And I want you to fill in the parts of this. So we have a turbine. That's the part that gets spun around by the water, or maybe the wind or something like that. We have the shaft that's connected to the magnet. And we have the all-important part here, the magnet. And we have a metal coil. That's our coil of wire right there that's going to have the electrons in it that start moving and create the electricity. So here's a couple of other examples of electric generators. We have, again, a hydroelectric power plant where it's the water moving through this dam that's making those turbines spin around. We have wind generated power where it is the wind that's turning these windmills and creating and moving a magnet in that way, which is generating our electricity. And you might even have one of these in your house, an electric generator, right? And in that case, it's a gas-powered engine, and the gas-powered engine is making a motor spin around. and turn a magnet in a coil of wires, and that's how you get electricity to power your house when your power goes out. So there's a few different examples of where it's used. Very important stuff here. Now the other side of this is the idea of an electric motor. So notice that with what we've been talking about up to this point with electric generators is the idea that you have to make the movement of a magnet into electricity. We start with movement, we get electricity out of it. Well, electric motors, these guys right here, is the exact reverse of that. An electric motor is going to use electricity to create movement. It's the same thing, just put in reverse. So this creates movement by running electricity through a coil of wire with a magnet in it. The whole idea here is that now we can take that electricity we have and we can put it back through this system and get movement out of it. Well, why would we want to do that? Well, for all of these kind of things. So remote control cars, or a fan, or a DVD player, the part that spins around. What you want to think of, I've given you a couple examples here, but I bet you could think of 100 other examples. Anything that works with electricity and has something that moves is an example of an electric motor. Anything. So a clock with little hands on it that moves, something like that. Anything, like I said, anything that uses electricity to make something move. So not necessarily your TV, because you don't really have anything moving there, but I don't know, your phone, the vibration of your phone is a little electric motor in there. So anything that uses electricity to make something move is an example of an electric motor. So I've given you several examples now. I would like you to write down 2 examples of each of these. You should see this little spot on your notes. I want 2 examples of electric generators and 2 examples of electric motors. All right, so there you have it. Those are the basic things that you need to know about electromagnetism. So, thing 1, magnetism is electric charges all pulling in the same direction. We learned about Faraday's law of induction. The changing of a magnetic field can create voltage. We learned about electromagnets, which is basically the reverse of that idea, which is that by running electric current through a wire, you can create a magnetic field. We learned about electric generators, which creates electricity by moving a magnet through a coil of wire. This is basically the idea of Faraday's law of induction. And we learned about electric motors, which again are just the same thing but in reverse. This creates movement by running electricity through a coil of wire with a magnet in it. We'll do a whole bunch of experiments with this in class this week, and I will see you then.